Hi everyone, this video is going to focus on discussing some of the basics associated with oxidation reduction reactions. So in this video, we're going to cover the following topics. One is, first thing we're going to talk about is the definitions of oxidation and reduction. And then followed by that, we're going to understand how to measure standard reduction potentials and how does this standard reduction potential stuff vary between non-biological reactions and biological reactions. And then the last part is measuring potentials under non-standard conditions. These are some of the topics that will be covered in this video. So first thing, we'll start with the definitions of oxidation and reduction. So in this topic, there are three definitions. We're going to go through them one by one. Here's the first definition. The first definition says that oxidation is gain of oxygen atoms and reduction is loss of oxygen atoms. And this is the definition that you may have seen in some general chemistry and organic chemistry classes, where here we've taken propane as our example. Propane is C3H8 and it's reacting with oxygen. And when it's reacting with oxygen, it's getting converted into carbon dioxide and water on this side. Here, I want you to pay attention to the propane itself, which is C3H8. It contains no oxygen at all, atoms at all to begin with, and then it undergoes the reaction with 5 molecules of oxygen. And then on the other side, if you see here, the carbon atom is now attached to 2 oxygen atoms, and then the hydrogen atom is attached to 1 oxygen atom over here. So that tells you that carbon has gained oxygens and hydrogen has gained oxygen. And this tells you that the carbon and the hydrogen have gotten oxidized, or we can say that the propane has gotten oxidized to produce CO2 and water. So the first definition here applies only to gaining or loss of oxygen atoms that is present in that we can see in certain reactions. Okay. The second definition deals with hydrogen atoms. Here we can the way it is defined is oxygen is defined as loss of hydrogen atoms and reduction is gained as the gain of hydrogen atoms. And this is again something that we usually see in organic chemistry. So in this case, we have chosen propanol as our example compound. Propanol is an alcohol. As you can see here, it has an OH group over here. And then at the end of the reaction, it's getting converted to an aldehyde, which contains this C double bond O H group over here. So I want you to pay attention to this particular carbon here and then this particular oxygen here. And I want you to see what is happening before the reaction. Before the reaction, you can see that the carbon is attached to 2 hydrogens, and then the oxygen is attached to 1 hydrogen. And then after the reaction is over, we can see that the carbon is attached only to 1 hydrogen, and the oxygen has lost that 1 hydrogen it was attached to begin with. So what we are seeing here is the loss of hydrogen atoms that is happening in the propanol. And because of that, we say that the propanol has gotten oxidized to become propanal, which is the aldehyde. Okay. And also, if you pay attention to the oxygen here, the oxygen has no hydrogens attached to it here. But if you look on the product side over here, you can see that it's attached to 2 hydrogens. So we can say that the oxygen has undergone reduction. So one take-home message from oxidation reduction reactions is that anytime there is an oxidation reaction happening, in the same reaction, there's also a reduction reaction happening. So when you combine these two, oxidation and reduction together, that's why these reactions are called as redox reaction, because it has both oxidation and reduction happening in the same reaction. Okay, so we've talked about 2 definitions, and just to push this point a little bit further and how this may show up in an organic chemistry class, if you look over here there are different functional groups of compound. We start with alkanes, then we have alcohols, then we have aldehydes and ketones, and then we have carboxylic acid and carbon dioxide. So these arrows, the downward arrows, are showing that we can convert alkane to an alcohol, alcohol to an aldehyde, and aldehyde to a carboxylic acid to a carbon dioxide. As you go through this process, you will see that these molecules are gaining oxygen atoms and also losing hydrogen atoms. Therefore, as you go from the top to the bottom, as you keep converting these functional groups from one to the other, this indicates higher and higher oxidation. That is, alcohol is, when you compare an alcohol and an aldehyde, aldehyde is more oxidized compared to an alcohol. A carboxylic acid is even more oxidized compared to an aldehyde. So we can see that this is happening. And these are all based on our first 2 definitions. And if you go back in the reverse direction, going from carboxylic acid, say, to an aldehyde, that process is called reduction, because now we're going to lose oxygens or gain hydrogens. When that is happening, we call those processes as reduction. So if you go one way from top to bottom, we're undergoing more and more, getting to more and more oxidized compounds. And then if you go from the bottom to the top, we are getting to more and more reduced compounds. Okay, so this kind of is an application of the first two definitions that we talked about. Now the question is, what if you have reactions that don't involve either loss of hydrogens or loss of oxygens or gain of oxygens? None of this is happening. So how do we create a definition that is much more universal, that is applicable to all compounds? For that, we are going to use definition 3. Definition 3 is much more of a universal definition. In this case, we're going to say oxidation is loss of electrons and reduction is gain of electrons. Because all compounds contains electrons, whenever they undergo oxidation reduction reactions, it's easy to apply this definition, because as long as you can keep track of where the electrons are going, we will be able to figure out whether there is oxidation or reduction reaction happening. Okay, so in this case, I've chosen an example where we have this copper solid, and it is reacting with the silver ion, which is in an aqueous solution. And then at the end of the reaction, we end up producing copper 2 plus ions in aqueous solution, and then we have silver solid present in that at the end of the reaction. Okay, so let's create a visual for how this might happen. So I'm going to show you a test tube here. So this is a test tube, and you can see this brown piece of stick-like thing that is sticking into the solution. That's the copper wire, and it's a solid. So that is pretty much indicative of this guy right here. And then now this solution here, this colorless solution here, is silver nitrate, and in silver nitrate, the silver ion is present in Ag plus form, so that's indicative of this Ag plus right over here. Okay, so now we've mixed them. We're going to wait a little while, and then we're going to see what is going to happen to this particular reaction. So let's see what happens. So now we've set it aside. Now here comes we waited for some time, and then you can see that the same tube, now the solution has turned blue here. So this is a blue colored solution. Now you can see that some of this brown copper wire has changed into some sort of grayish compound here. So that's basically our silver. Now the silver that is over here, that we're talking, the silver that's deposited on top of the metal, is what is shown here in this chemical reaction. Now this blue stuff, why is this blue in color? The reason why this is blue in color is because some of the copper that we started with, the copper metal, has dissolved into the silver nitrate solution to produce these copper 2 plus ions, which are blue in color. So this is an example of an oxidation reduction reaction, and I'm going to explain to you in the coming slides how do we know that this is an oxidation reduction reaction. Okay, so I'm going to explain that. So this is the end result of a reaction. So now we're going to explain how this actually works out. So when you're going to look at a reaction like this, what I suggest is breaking this overall reaction into two halves. So I'm going to separate our copper over here and then try to make a connection with this copper 2 plus on this product side. So that's one connection. And then the second connection that I'm going to make is take the silver plus ion and then make a connection to silver, because if you want copper 2 plus on the product side, it should have come from copper metal on the left side, and then the silver plus ion on the left side is the one that is going to generate your silver solid on the right side. Okay, so I'm going to separate those two reactions out, and I'm going to write it like this. So once I've separated the copper reaction, I can write it as copper solid now becomes copper 2 plus solid plus. So then I ask myself, if the copper solid would have converted into copper 2 plus, then what would have caused that? And then if I think a little bit, then I realize that copper metal, which has a 0 charge, if it's going to become something that's 2 plus charge, usually a plus charge indicates that a loss of electrons has happened. So now the question is, depending on the number of charges that are there are 2 plus charges. That means that this copper over here would have lost 2 electrons in order to make this copper 2 plus ion. Okay, so this copper 0 has lost 2 electrons. So because it has lost 2 electrons, we say that the copper solid has undergone oxidation, or we say that copper solid is oxidized to copper 2 plus aqueous. And when it's doing this, it has lost these 2 electrons. Okay, so that's what is happening. So what we are learning here is that the copper has gotten oxidized, the copper metal solid has gotten oxidized into copper aqueous. So this should not say solid, it should say aqueous. So this should be aqueous, sorry. So it is converted into copper 2 plus aqueous. Okay, so this is an oxidation half of the reaction. So we call it the oxidation half reaction. And then the other half is the silver part, where you have the two silver ions, and the two silver ions are getting converted into to silver metal. And how would have this happened? This would have happened only if the silver ion here, which has a charge of +1, if it gained one electron, it would produce one silver ion. And if another silver ion gained another electron, so that's a total of two electrons, then they would have become two total silver solid atoms. Okay, so because the silver ion has gained two electrons, we say that the silver plus is reduced in order to produce this silver solid atom. Okay, so this is how we are figuring out what is going on in this copper silver reaction. And this definition is based on the gain and loss of electrons, as we have highlighted over here. Okay, so this is what is going on over here. Another important point is, how can we tell whether a compound is getting oxidized or reduced? Typically, in our case, our copper to begin with was at 0 charge, and then when the reaction was finally over, it changed into copper 2 plus. So it changed from a charge of 0 to 2 plus. When your charge is changing to more plus charges, then that is indicative of loss of electrons. So in this case, that's the reason why we say that the copper 0 is getting oxidized to become copper 2 plus. Whereas in the case of silver ion had a charge of +1, and then that +1 charge got converted into 0 charge. And anytime you're going from a more positive value of charge towards more negative values of charges, that is indicative of gain of electrons. Because if you remember, electrons are negatively charged. So when you're gaining electrons, you're going to go towards more negative charges. So +1 to 0 is a gain of 1 electron. So that's an indicative of reduction. Okay, when you go to more negative values of charges or lower positive values, then that's indicative of reduction. Okay, so this is how you keep track of how the electrons are getting transferred in an oxidation reduction reaction. And if you want to use the electron definition, this is how you need to keep track of these charges. All right, so there are certain mnemonics, that is, these are like, funny phrases that you use to remember oxidation reduction reaction. So typically we say loss of electrons is oxidation, gain of electrons is reduction. How do we remember this? We remember this using this mnemonic that says Leo the line says GER, because Leo stands for lose electrons is oxidation, and then GER stands for gain electrons is reduction. So Leo the line says GER is one useful mnemonic that you can use to remember oxidation reduction reactions. There's another mnemonic that you can use, which is called oil rig, because we can say oxidation is loss. If you take only the first letters here, O, I, L, oxidation is loss and reduction is gain, we can easily remember this oxidation reduction reaction using this mnemonic oil rig. And here I've shown you the picture of an oil rig, what it looks like. So that should kind of help you remember what are the definitions of oxidation reduction reaction. So just to take stock, the definition based on electrons is probably the most universally applied, in the sense that you can apply it to all reactions, because independent of whether there is oxygen involved or hydrogen involved, there's certainly going to be, whenever there's oxidation reductions are involved, there is going to be loss of electrons or gain of electrons. So that's why this is much more of a better definition. Definition number 3 is what people use all the time. But when you take organic chemistry classes, or sometimes in biochemistry classes, if you want to understand oxidation reduction reactions, sometimes we're going to use the definition 1 and definition 2, because it may not be very easy to see the electrons being moved, but we can very easily track the movement of oxygens or gain of oxygens or loss of oxygens or gain of hydrogens or loss of hydrogens. That's a lot easier to do. So that's why we'll use those definitions. So that means we're going to be using all of these definitions depending on which context we're talking about, because we're going to use the easiest way to understand things. And wherever electrons are easily trackable, we're going to use the electron definition. Where electrons are not easily trackable, if we can track it using oxygens and hydrogens, then we can use definition 1 and definition 2. Okay, so that's an important thing here. And as we are talking about oxidation reduction reaction, one common thing that you will hear about, the terms that you will hear about, is this concept of oxidizing agent and reducing agent. So how do we understand this idea of oxidizing agent and reducing agent? So we are still in the process of talking about this copper silver reaction. We know that this copper this reaction has two halves. One is the copper half reaction, the other one is the silver half reaction. And we learned in the copper half reaction that copper solid changes into copper 2 plus and it loses the 2 electrons. Now the question is, when the copper loses the 2 electron, where does the 2 electrons go? These 2 electrons are going to be accepted by the 2 silver ions which are located over here. So what we are learning is that this copper, which is undergoing oxidation, is actually giving the electrons to help the reduction. So it's helping the reduction reaction. So because it's helping the reduction reaction, we can say that this copper metal, which is donating the 2 electrons, is basically an agent that helps in reduction. So that's why we call this copper as the reducing agent. So if you want to remember it in a short way, we can say a compound that is getting oxidized will serve as the reducing agent. And then the same thing can be said of the silver ion. The silver ion, which is accepting the 2 electrons, is also making the copper keep giving electrons. Okay, so therefore the silver ion, which is getting reduced to silver solid, that silver ion is going to be considered as the oxidizing agent. So just to summarize, a compound undergoing oxidation is the reducing agent. A compound undergoing reduction is the oxidizing agent. So once we figured out which compound is undergoing oxidation, then that compound is going to serve as the reducing agent. Once we figure out which compound is getting reduced, then that same compound is going to serve as the oxidizing agent. Okay, so these are some definitions that you're going to come across. Now the question is, why are oxidation reduction reactions very important? Because we are obviously looking at it. They must have some value to it. Why should we care about oxidation reduction reactions? One of the main reasons why we care about them is because oxidation reduction reactions are a source of energy. Okay, in nature, many of the naturally occurring reactions that produce energy, those are going to be oxidation reduction reactions or redox reactions. And we actually exploit them for making batteries. So the batteries in your cell phones, the batteries everywhere you use batteries, we are exploiting redox reactions. And those are the reactions that are providing us the voltage that we need to run our cell phones or batteries or whatever we want to use the batteries for, is going to be very helpful. And when you think about biological stuff, there are metabolic processes, and the metabolic processes are like glycolysis, TCA cycle, electron transport chain. All of these processes involve lots and lots of oxidation reduction reactions, and then they are the ones that are responsible for producing ATP in our body. So basically, these oxidation reduction reactions are very, very good sources of energy. Okay, and these oxidation reduction reactions are also very important when you want to they play a role in antioxidant compounds. These antioxidant compounds are very important because they help in scavenging what are called reactive oxygen species, which are pretty dangerous. And if you have a lot of them, then they can end up causing all kinds of disease states like cancer and things like that. So in those cases, also your oxidation reduction reactions are pretty useful. And then a third class where these oxidation reduction reactions are useful is you can use these oxidation reduction reactions to synthesize new compounds and new materials that we can use for various applications. It doesn't have to be biological. It can be used for other applications as well. So if you want to make new materials, then these oxidation reduction reactions are very, very useful. Okay, so that's why these oxidation reactions are very important. So now I said in the beginning that these oxidation reduction reactions are very important sources of energy. Now the question is, how do we actually figure out the energy that is produced from these reactions? Okay, we're going to talk about this in the next few minutes. But before that, I want to give you some sort of foundation so that it's easy for you to understand what we're going to discuss in the next few minutes.